Dominic Di Toro, and it's a pleasure to be here, really. I enjoyed this. I haven't thought about sediment flux modeling in a while, so it was fun to look back on it. And unlike what Carl did, I'm going to try and give you more of a historical look at the problem and then some of the key ideas. And you'll all be playing with codes and programs and all the rest of it. But it's interesting, how do you actually learn how a model works? I mean, how do you actually develop an intuition about a contraption that you put together? The first sediment flux model I built was in the late 70s, in the early 80s, when I was getting interested in geochemistry and had a very nice chemical equilibrium program. And I put everything I knew about it into that model. Every bit of geochemistry I could find in textbooks, I crammed into that model. I spent 2 years playing with that thing. I could never get it to look like any sediment anywhere. The reason was I had given myself yet another problem. There's the real world, I didn't understand it. And then I made a model that was so complicated, I didn't understand that either. So I went from one problem to two problems. So what I'd like to do with this talk is to try and give you the key ideas that are underlying the sediment flux model, so that when you see it doing odd things, you'll have at least some place to start. Secondly, some of you know that I pretty well wrote down everything I know about this subject in a textbook that's still available, actually. I checked on Amazon, and it's under $100 for used books. Nowadays, that's cheap. So if you really want to read in gory detail what goes on, and I've included the table of contents at the end of the talk, which will be on the web so you can see what's in it. So, sediment flux modeling. The original problem that was looked at was sediment oxygen demand in the early days of dissolved oxygen modeling. And the problem was that the way DO models were built in the first generation was that the water column was the control volume, and the sediments underneath were regarded as an exogenous source. And so you just specified what the flux was coming out of the sediment. So if you were fitting some dissolved oxygen profiles, what you would do is you'd go out and make some measurements of SOD, and you get numbers like 1 gram per meter squared per day or 2 grams per meter squared per day, and it sort of fluctuate around. And then you'd run your model, and if it didn't fit, you'd change the SOD a little, and you'd diddle around, and you could get the line to go right through the data points. After a while, we got so good at this that I began to think, if I see a line going through every data point, the question is not whether the person cheated, the question is, how did they cheat? So the trick was to build a model that reduced the degrees of freedom so that there aren't so many adjustable parameters that no matter what you end up, whatever data you have, you can get the thing to just go through every data point. So the critical point was to try and build a model where the sediments were part of the calculation, not exogenous variables. So I'll give you a brief tour of a few sort of famous experiments that set the stage. One of the most interesting experiments was done by Gordon Fair and Harold Thomas in 1941. He was the professor of, it was called sanitary engineering, of course. And he wore a stiff collar and a bow tie. I mean, he looked like the 19th century, lawyers. Gordon Fairmore, I forget what the environmental engineering textbook is. But anyway, it's Gordon Fair. Here's the experiment he did. They made up a sediment with sludge and some diatomaceous earth, and they put various concentrations of it in a set of reactors, and then measured the oxygen consumption. And what they found was that if they measured the SOD in grams per meter squared per day, the normal units, that at various times, this is the time at t equals 0, this is then 100 days, 200 days, what you saw was that on the y-axis was SOD, and on the x-axis was the initial volatile solids that was added to the reactor. You would imagine that the SOD would be proportional to the organic matter that you add. Right? I double the organic matter, I've got twice as much mineralization, you'd expect that I'd have twice as much SOD. Ain't what they found. What they found were these curves. Another experiment that was done in some Green Bay sediments many years later, where the COD of the sediment was measured, and they got the same sort of sloping behavior. Anybody got an idea what's going on? take a close look at the top of the experiment. It says gas trap. What was happening was that some of the material was coming out as methane and bubbling out of the... And Fair was a smart enough guy to actually have trapped that. So the first indication is that it ain't so easy. It isn't just the amount of organic matter that mineralizes. You got to worry about what happens to it on the fly. And it's not only in diatomaceous earth and sewage sludge, it's actually in real sediments. The problem with this is, of course, is you don't know what the x-axis is in a model, or at least you got to deal with that problem. If you're going to build a model that's just those curves, you have to have an idea of what the organic matter is. In 1986, there was a meeting at the EPA Athens lab, and one of the speakers gave a talk. He was a microbiologist and gave a talk, geomicrobiologist, gave a talk about how carbon is mineralized in sediments. And this is the diagram. And you notice it's hopelessly complicated. I mean, you have organic matter, you got acid fermenters, then you get short chain acids, some aerobic respiration, you get chemosynthesis, carbon dioxide's coming out of here, you also have some anaerobic, blah, blah, blah. And in fact, if you look at a table of all the way that organic matter can be mineralized, you end up with all of these reactions. So organic matter can just be respired directly to CO2. You can get sulfide oxidation from -2 to +6 oxidation states. You get oxygen consumption, nitrification. You get ferrous to ferric iron oxidation. You get methane production. And you also get then... And so he said, I have a curve to show you the present state of the knowledge of the relationship between SOD and all of the reactions. I nearly fell out of my chair. So that was the state of what was understood in 1986. That was helpful. I thought that was good. So years later, we started to work on Lake Erie, and it was clear that we needed to be able to calculate what SOD was going to look like. And so the basic idea of this kind of model was this. The flux of organic matter to the sediments is the source of what's going on. That was obvious. But the next idea was that the fluxes are proportional to the stoichiometry of decaying organic matter. So long as methane isn't produced and you get some escaping, it's not a terribly bad suggestion to think that maybe you just have, if you know how much, if you think that organic matter is being mineralized to CO2 and ammonia, then you can calculate that the ratio of sediment oxygen demand you should get to the ratio of ammonia flux that comes out if you make the following assumptions. Organic carbon is oxidized to oxygen, just straight COD. And ammonia is conservative. You don't worry about nitrification. Then what you get from the Redfield ratio is that the ratio of the SOD flux to ammonia flux should be 15. Okay? See the idea? I take organic matter, I oxidize it completely. That's the oxygen consumption. The nitrogen that gets released, I do nothing with it. I let it all just pour out. Okay? Ask questions, gang. Or nod at least, otherwise I'll pause. Good, he's nodding. So here's some data. Here's a cross plot of oxygen, SOD on the y-axis, 1/10 to maybe upwards of 10. It's pretty high. And then on the x-axis is ammonia fluxes. And there's 15. Well, you can see the data's got a little jumble in it. So maybe all the ammonia flux isn't coming out. Maybe some of it is being nitrified, in which case the denominator would be smaller. So if you take half the ammonia flux as being what's coming out, the other half is nitrifying and going away, you'd think 30 is the right answer. Or if you think maybe that the organic matter isn't quite, that some of the oxygen-containing material is being buried in some way in the deep ocean, maybe the fraction ought to be half. So those are factor of 2 uncertainties. This is a lesson for you youngins. That's what's really going on. The line ain't straight. And so when you approach a model, it's useful to have an idea in your head, but it's also, see, same data. Isn't that interesting? So there's a square root relationship between the SOD and the ammonia flux, and one of the things we should be looking at is what's going on with that. So that was the state of the game in the early developments of these models. So this is the current framework that we started with, and the normal way of building sediment models, by the way, is multiple layers, 10 or 20 layers in the vertical. At the time we started to work with the Chesapeake Bay model, there wasn't the computing power to add another 10 or 20 layers underneath every bottom layer, A. B, it wasn't actually clear that you needed all of that. The idea that many people still have is that the flux of material to the water column is the concentration in the pore waters times the dispersion coefficient, the diffusion up. And that turns out not to be the causal. The cause is the flux, organic matter comes to the sediment. There's only two places it can go. It can either be buried or it returns in some way. So the cause of all sediment fluxes is the source of material into the sediment and then the mineralization. That's the mass balance, right? And that's how we connect it to the water column. So from that point of view, then maybe you don't need to know what the gradients are very specifically. You don't have to model the curvature and all the rest of it. Maybe you can get away with simply building a model that's got the two layers. And the reason you need two layers is that the chemical reactions and the biological reactions that occur in the aerobic layer, nitrification, for example, are quite different than the reactions that occur in the anaerobic layer. So the way the model was conceived was as follows. One, there is flux of organic matter. Think of it as Redfield organic matter. That stuff. Remarkably, the stoichiometry of organic matter is actually quite constant. Detrital organic matter, algae, varies by a factor of 2 maybe. Phosphorus is a bit more variable, of course. So Redfield organic matter settles to the sediment. Reactions occur. In the anaerobic layer, you release hydrogen sulfide, methane, ammonia, phosphate, and silica, because those are all components of organic matter and/or components of the sediment that get mineralized. And then finally, the stuff gets transferred up, but it has to get through the aerobic layer, and so things change. So the game is to try and model the reactions that are occurring in some sensible way and not worry too much about the vertical structure. Clear the logic? I don't think, in fact, we couldn't afford when we built this thing more than a couple of layers. Okay, so the first thing you need to specify is the kinetics of the decay of organic matter. This has been studied for a long time, and the name that you should know is Robert Berner, who was a famous geochemist at Yale. This model is, what's the date on this? It's the mid-80s, I think. No, earlier. Anyway, these are experiments that they did with algae and watched the decay of particulate organic carbon as a function of time. So here is a plot of organic carbon in grams per liter in days out to 400 days, and you see a very fast drop. And then if you look further out, you see a slower drop. If you plot the things on semi-log paper and you look at the rates, you see that there is a very rapid drop and then a much slower drop. And then finally it settles to just essentially a conservative. The reason there's organic carbon in sediments has got to be that there's a fraction that doesn't decay away. Otherwise it would all mineralize and there'd be hardly anything there. We wouldn't have any soil in the world, right? So there has to be a very resistant component of organic matter. So that's what the G model is about. Basically what you see is that there's a rapidly decaying fraction, G1. This is not our invention. This is Berner and company, the G model. He had up to G6. He was interested in how coal formed and petroleum, so he had 6 cascades. We thought 3 was enough. And so the way we've got it built is that there are 3 forms of organic matter, and the fractions are determined by a fair amount of data that has been looked at over the years. And so here's how the 3G model thinks of organic matter. It has 65% G1, 20% G2, and 15% G3. These are numbers that have been tabulated, lots of examples in the book, and these are sort of in the middle. The reaction rates are 0.35 per day. By the way, for those of you who don't know what a first-order reaction rate is or how to understand it, you can understand percentages, right? That's easy. 65% of this stuff is G1. Engineers have to have a feel for the numbers. You have to have a numerical sense for what they mean. So how do you think of a decay rate? What does it mean to you? Give me a definition other than per day.
3.5% of the stuff goes away in a day.
Correct. It's the fraction of material that decays away in one day. So that would be right. Yes, 3.5% per day. Correct. Okay, so when you see a first-order reaction rate, divide by 100, and that tells you the percent per day. So you can see that G2 is like 0.1% per day, so it's reacting very slowly. Another way to think of it is you just take the reciprocal of that, and that's the time it takes to get to 37% of the original, so 28 days and 55 days. And then finally, the temperature corrections, and sanitary engineers developed the oddest temperature correction in the world. It's this theta dependency. And the idea is that the reaction rate at any temperature, say 10 degrees centigrade, is the reaction rate at 20 degrees centigrade theta to the 10 minus 20, or 10 to the minus 10. The Q10s, which are the ratios of 10 to 20, is what the biologists use. That's a number you can keep in your head. And a reasonable for the kinds of 0.168, which is commonly used for reaeration, that's about a Q10 of 0.5. So the reaeration rate will double. On the other hand, look how much more sensitive the anaerobic decay mineralization rates are. This is G1, and this is G2. So it's a fourfold change going from 10 degrees to 20 degrees. So diagenesis shuts down pretty much in the winter. That's a very important point. So the production of organic matter is shutting down in the winter by a lot. Remember that, point number one. Okay? Also, because G2 decays rapidly in a sediment, most of the reactive material in a sediment isn't G1. It's being mineralized very rapidly. So if you take a chunk of sediment and pull it out, what you've got almost entirely is G2 and G3, right? And you'll see that when we look at some equations. So the purpose of this talk is to try and build some first-order sort of structural understanding of how this model works, and then you can fool with it and get some more insight. So that's another important point. Diagenesis shuts down at 5 degrees. Just gone. It's another 0.2. Okay? Comments? No? Okay, mass balances. So let's build ourselves a model for the decay of particulate organic carbon in a single volume. We don't worry, it turns out. You can convince yourself that even if the decay of G1 and G2 is relatively rapid in the aerobic layer, the thickness of the aerobic layer is millimeters. The thickness of the anaerobic layer is 5 to 10 centimeters. So if you do a mass balance proportionation, the amount of organic matter that's decaying up here, you can just forget about it. It's all happening because there just isn't enough there. So we don't worry about it. You could worry about it, of course. It doesn't change anything. So we don't distinguish between H1 and H2, the aerobic and the anaerobic layer. We build a mass balance simply on the total depth of the sediment.